Welcome to the last part of Week 8, Lecture 8, EEE 157, Communication Systems and Networks. In this part of the lecture, we will be talking about the encoding process. How do we translate a quantized signal into its bit sequence? Okay, so there are three different basic techniques of encoding: the pulse code modulation, delta modulation, and the differential pulse code modulation. There are other more developed encoding techniques out there, but they're for more advanced uh, courses, right? But we will just be talking about the three basic ones of the encoding process, right? So, without further ado, what is encoding or waveform coding? This is the third stage of your analog to digital conversion. So we have a sampled and quantized analog waveform. We want to represent it into bits, and we can now store it in a computer. Okay, the bit sequence and its output can be used to reconstruct the waveform in the digital domain. We have a series of bits. Depending on the encoding technique, we can recreate the waveform, the analog waveform in our computer. Okay? And this is a brief summary of the three different techniques. So it's a wall of text. So let's go through them one by one, okay? The pulse code modulation encodes the waveform into integers. So commonly integers where 0 corresponds to the lowest level. Okay? And it does not use feedback compared to delta modulation and differential pulse code modulation. This is a direct application of the quantized signal. So when we quantize the signal, we're mapping it into symbols. We translate the lowest level symbol to the 0 integer and the highest level symbol to the highest integer that the computer can represent. Okay? So if you have a 4-bit computer, the highest integer is 15. If you have an 8-bit computer, the highest integer is 255. If you have a 1-bit computer, it doesn't exist anymore, your highest integer is 1. Okay, so you map that naturally from the lowest level to the highest level. You map that naturally and you can recreate your waveform. The delta modulation offers a more simple implementation by using only a 1-bit quantizer. Okay, so it boasts simplicity in implementation. However, it uses more bandwidth. So we'll talk about that later in this lecture. Okay, so the bottom line here is that the delta modulation technique uses a 1-bit quantizer only. Your PCM needs larger number of bits, but for delta modulation you need only a 1-bit quantizer, which is easy to implement. So you will see how it works later. How can a 1-bit quantizer uh, encode a waveform, right? Finally, your differential pulse code modulation employs what we call a tapped delay line to predict the message behavior. So it takes advantage of the redundancy when we're sampling signals. It takes advantage of that. And from these sampled signals here, it will try to predict the message based on the sampled signals. So once it predicts that, it will use a unique bit sequence. Right? This bit sequence will enable the receiver to reconstruct your differential pulse code modulated analog signal, and you will be able to more accurately represent your your analog signal rather in the digital domain. However, DPCM is the most difficult to implement in hardware due to its tap delay line. Okay, it uses a tap delay line, so it will have a more complex implementation in hardware. So bottom line, between the three, right, PCM is the most balanced in terms of complexity and transmission bandwidth. And if you have a large transmission bandwidth and you don't want to have a more complex system, use the delta modulation. If you are limited in terms of transmission bandwidth, okay, you need to increase the system complexity so that you can transmit your DPCM signal. Right? So you can fit more data into this transmission bandwidth even if it's limited. So you can use DPCM for that. So that's the difference between these three. Okay? So bottom line here is that if you want a more bandwidth saving encoding scheme, you'll need to have a more computationally complex encoding scheme. Okay, so the pulse code modulation, you have seen this already. It's going to map your bit representation based on the lowest level and the highest level. So it's just a natural mapping between your signal level to its integer representation. Okay, so an example is shown here where you have only 2 bits of quantization power. Okay, you have four signal levels from S4 to S1. The lowest signal level is mapped to the the zero integer, which is represented by the 00 bit. Okay, and the next level would be 01, which is represented by integer 1, and so on and so forth, until your number of bits cannot represent the signal level anymore. Okay, so to visualize that, here is your waveform. Okay, so if you have a 2-bit PCM encoding, you can recreate your digital signal in the digital domain right here. As you can see, there's a large error, but if we use more bits, we have a more smoother signal right here. Okay, so if you use 16, maybe even 32 bits, you won't see the difference between these two signals anymore. Okay, so if you have more bits, you can use a more accurate representation, but a more expensive quantizer is needed because you need to have a greater number of bits. Okay, it's easy to make a 32-bit system and a 64-bit system. Most computers now uses 64 bits. Okay, to represent an integer, can easily recreate. It's approximately analog already. You have 64 bits. That's a lot of quantized levels. Okay. Okay. So we can see the difference of having larger number of bits in images. So as you can examine between these two images, the image on top uses only 2 bits to represent the image. The image at the bottom, you have 8 bits. For the 2 bits, you can only see or define the number or the different signal levels here. Maybe this purely white part of the image is represented by 3. This purely dark part is represented, wait, let me change the color of, okay, this purely dark part here is represented by 0. This darker part here is represented by 1, and the light gray part here is represented by 2. And you can only identify these different colors. But when we increase the number of bits, you can't distinguish the signal levels anymore, as you can see here. Okay, the bright part here could be represented by 255. The darkest part, I don't see any very dark part here, but the darkest part could be represented by 0. Okay, and as you can see, the resolution of the image, compare this part to this part. As you can see, this part you can't make out uh, what's the information stored in this part of the image. But when you have an 8-bit image, you can see that, oh, those that part, they look like people. Okay, and this is how the uh, encoding works. PCM encoding works. Okay, increase the number of bits, you can better represent the original signal. The problem here is that it uses more memory in your computer. Okay, next is the delta modulation. Your waveform is sampled at a higher rate to increase what we call the correlation between the present and the past samples. Okay? So it only uses 1 bit to represent the signal, okay? But that doesn't mean that it uses less memory. On the contrary, it actually uses more memory to represent the signal. That just because it is sampled at a much higher rate compared to what PCM samples. Like, even if it uses only a 1-bit quantizer, if it's sampled at a higher rate, you can expect it to have a larger transmission bandwidth. Okay? So how does delta modulation work? If the output is bit 1, that means the signal increased from the previous value to the present value. If the output is bit 0, that means the signal decreased from the previous value to the present value. So it is represented by a staircase right here. It looks like the signal is a staircase, okay? And you have a series of ones at the start to represent that the signal is rising. So the output of your delta modulation here will be 1, 1, 1, 1, 1, 1. And that means the signal increases from its current value to its final value. Okay? At this point, it encounters a 0. So that decreases the signal from here to here. And then 2 ones here. So you increase the signal and so on and so forth. Okay? So that's how delta modulation works. A series of zeros, that means your signal will be decreasing and so on and so forth. Okay? So in contrast to your pulse code modulation, where the signal level is encoded directly to the bits, your delta modulation uses the bits to represent a change in the signal. Okay? So your present sample, let's call it m sub k, is related to m sub k minus 1, okay, plus delta, plus or minus delta. Okay? So if your bit is 1, then you will add to that delta. You'll add that delta rather to your previous sample. If your bit is 0, then you reduce that delta from your current sample. Okay? So that's how you approximate your signal using delta modulation. Okay? So we can see how you need a larger sampling rate here. So if you have a larger sampling rate, you will be able to track your original signal properly. Okay, what's the downside to this delta modulation? It's actually just a simple algorithm that uses or that represents, instead of representing the sample directly, it represents the change between two samples. Okay? So your bit 1 is decided by the difference between the current sample and the previous sample. So quite simply, if the difference between the current and the previous sample is positive, then you output bit 1. If the difference between the current sample is negative and the previous sample is negative, then your output is bit 0. It's that simple. It's easier to implement compared to PCM. Okay? The downside is that it has two limitations. If your sampling rate is very slow, you have what we call the slope overload distortion. The slope overload distortion happens when your delta modulator can't keep up with the signal. Okay? So you can't keep up with the signal. What will you do? You can increase the step size. If you increase the step size, it will move faster and will be able to approximate the signal better. Okay? Or you can increase the sampling rate. If you increase the sampling rate, okay? If you increase the sampling rate, then, oops. Okay. If you increase the sampling rate, then maybe it can be easier to keep up with the original signal. But if you increase the sampling rate too much, or if you increase the step size too much, then you get granular noise. So the granular noise is the oscillating behavior of your delta modulator because of the slow change in the signal. So your delta modulator, if you zoom in here, your delta modulator will have an oscillating uh, problem here because of the nature of your delta modulator. Okay? So this happens if your step size or your sampling period is too fast. Okay? And you get this granular noise here. So we can better, you can see here that your signal is well approximated. It's better approximated compared to this signal. However, there is an inherent noise that you will hear if you try to play it. Okay, if you try to hear the signal, if this is a speech signal, you will hear that granular noise. Okay. Finally, the differential PCM. Compared to delta modulation, the differential PCM does not just use the immediate past value, it uses more than one past value of the input to predict the output of the signal. How does it make a good guess of the signal? It uses Taylor series, basically. The Taylor series, we can predict the output after some time step delta t by using the Taylor series. Okay? So where does the previous samples come in here? You have derivatives. Okay? When you're using derivatives in the digital domain, they become this. Okay? Let's see. So let's say these terms, the higher order terms will disappear first, and look at the first order approximation of your Taylor series. If we let delta t be the sampling period, okay, and we assume that delta t is small enough, your first order approximation looks like this. Okay, this is your current or your future sample. This is your current sample, and it's related to the previous sample by this equation. So the first derivative looks like this approximately. Current sample minus previous sample divided by your time step. Okay, so where did this come from? Recall that the derivative is basically delta for this, in this case it's delta m over delta t. Delta t is t sub s. Delta m is the difference between the current and the previous sample. Okay, so this term here is just this term right there. Ts cancels out, and you'll get this equation to predict your future value based on your current value and your past value. Okay, so this is the formula that you'll use. You can use a system with more memory, but you'll have a more complicated implementation. Bottom line here is that if you use more memory, you're using or you have a more complex implementation. But with more complex implementation, you can better you can reduce the transmission bandwidth of your differential PCM technique. Right? So in general, you have the nth order approximation looks like this. Your a sub I here is what we call the weight. Okay, so it's what we call the weight, and you don't need to know how to determine this. You just need to know how it works. Okay, so we have different weights for the different past samples. Okay, by sizing the weights correctly according to Taylor series, we will have a predicting filter that we call it a prediction filter, or a predictor, that has an accurate grasp of what's the next output is. Right? And we will encode that. So the difference between this and this, we will encode that as the bit. Okay? Or the bit sequence rather. That's the input. That will be the input to the quantizer. The difference between this and this. If your signal is if your prediction filter is very accurate rather, then the difference between this and this will be very small. And if it's very small, it needs less bits to represent itself. Right? Even if we have a small sampling rate, we can represent the output of your encoder as a small number of bits only. Okay? And we are using these bits, the bit sequence, we will be able to accurately represent the output signal by using the same prediction formula at the receiver. Just a note that the delta modulator is actually, sorry, not a 1-bit version, but a 1-memory version rather. It's the same. It's basically a differential PCM technique, but you're using a single memory only. You're using one past value to approximate the next value. Right? So that's the difference between delta modulator and your differential pulse code modulator. Right? So just to visualize, if you use more memory, you can more accurately represent your signal. So you can see here, using DPCM with memory of 2. Here's DPCM with memory 4. You can see that it's not really obvious here, but if you take the difference between the two, you can see that the power of the quantization noise, or the noise in the second part, is less than the power of the noise here at the image on the left. Okay, so if you have more memory, you have a more accurate representation even with the same number of bits in the quantizer. For these two, you have a 2-bit quantizer. Okay, you will see this in the simulation. Okay, it uses less bits than PCM, therefore you're decreasing your transmission bandwidth. Okay, but it's still prone to slope overload distortion if the sampling rate is low. So this is still similar to delta modulator. Okay, since uh, you're encoding, you're quantizing rather, you're quantizing the difference between your current value or the future value with the predicted value right here. Okay, so if you're encoding your waveform that way, expect that you will be prone to slope overload distortion. If your sampling rate, basically, if your sampling rate is very small, then you will have a hard time representing the signal in the digital domain. Right? So as you can see, it's very complicated. Bottom line here is that you can save memory if you're going to use differential PCM. Okay. So just to summarize, your analog waveforms can be encoded into bit sequences in different methods. You have different ways. I just presented 3 of those. More complicated methods are there, but they are more efficient. Especially, for example, the speech signal. I'm not an expert in speech processing, but analog waveforms are encoded into bits using the cepstral coefficients. And this is what phones use actually. Right? They use the cepstral coefficients to encode a speech signal, and it's a very accurate representation of a speech signal in what we call the cepstral domain. Okay, and if we use that, if we transmit that into bits, it's very efficient. Okay, but that's for higher courses, for more advanced courses. It's not for this one. Just an example. The process is complicated compared to DPCM, DM, and PCM, but the encoding is more efficient. So from there, you can say that there's a trade-off between the complexity of your coding scheme and the bandwidth, or related to the bit rate. So you can observe that. As we can see here, the PCM is the most complex, but it's the most efficient, while DM is the least efficient, but the simplest to implement. Okay. So the limitations with both delta modulation and differential pulse code modulation is the slope overload distortion, which happens if your sampling rate is too large. Rather, if you're sampling very slowly, which is not which is a no-no anyway for your even back in the sampling part of the lecture. If we have a slow sampling rate, it's prone to aliasing and other errors if you try to recover it. Okay? Unique to delta modulation is the granular noise. So when the sampling rate is too fast, then you will get some noise due to the nature of the delta modulator. Okay. So finally, your differential PCM can actually use any prediction filter, but if you use a prediction filter based on the Taylor series design, then you get a good prediction filter. And a good prediction filter actually decreases the number of bits that will be used by your differential PCM. Okay? And that is the end of this part of the lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Okay? Or you can email me or whatnot. Because why not? Okay? So if you have any questions, again, leave a comment in the comment section. Thank you for listening. See you next meeting.